Hi, welcome to the binomial distribution for large N. So let's say we have a coin which, when flipped, has a probability pH of coming up heads and a probability pt, which equals 1 minus pH, of coming up tails. If we flip this coin n times, the probability that it comes up heads exactly m of those times is something that we will write as p of m given pH and n, and it equals pH to the m power, 1 minus pH to the n minus m power, times n factorial over m factorial n minus m factorial. This is called the binomial distribution. The binomial distribution comes up in a wide array of contexts, both in science and in everyday life. If you'd like to see some examples, you can check out Why the Binomial Distribution is Important, available on this channel. In this video, we're going to look at the case where the coin is flipped many, many times. In other words, we're going to derive the large N limit of the binomial distribution. We'll take N as large, but we're not going to take the limit where N goes to infinity. We'll also assume that the average expected number of flips coming up heads, which is phn, and the average expected number coming up tails, which is 1 minus pH times n, are also large. We'll see that in this limit, the binomial distribution approaches a Gaussian distribution, also called a normal distribution. In this video, we'll assume you're familiar with the binomial distribution as discussed in the binomial distribution available on this channel. We'll also be using the results that the binomial distribution has a mean of nph and a standard deviation sigma sub m, which equals the square root of nph 1 minus pH. These are derived in the video Mean and Standard Deviation of the Binomial Distribution, so you might want to check that out. But if you're okay with accepting these results, you can go on with this video. Also, we'll be doing some math in this video, so there are some things that you'll need. You'll need to know some basic facts about exponentials, such as the fact that x equals e raised to the natural log of x, the fact that e to the x power times e to the y power equals e to the x plus y power, and also that e to the x raised to the power y is equal to e to the xy. Also, we'll be using Stirling's approximation for large factorials, so you might want to take a look at that. We will also be using a series expansion of the natural log, so the natural log of 1 plus x is equal to x minus 1/2 x squared plus 1/3 x cubed, etc., which is valid as long as the absolute value of x is less than 1. Okay, so with that, let's get started. So in this video, we'll assume that the number of coin flips n is large but finite. We'll also assume that the average expected number of flips coming up heads, phn, and the average expected number coming up tails, 1 minus pH times n, are also large. Let's see how the binomial distribution behaves under these assumptions. Okay, so we start with the binomial distribution, and we see that it contains these three factorials, n factorial over m factorial n minus m factorial. To deal with these, we're going to use Stirling's approximation. So Stirling's approximation tells us that n factorial is equal to the square root of 2 pi n times n over e raised to the n power times 1 plus terms that go as 1 over n. Now if n is large, those terms that go like 1 over n are small, and n factorial is approximately equal to the square root of 2 pi n times n over e raised to the n power. Now we're taking in our expression n, m, and n minus m as large, so we'll apply Stirling's approximation to the n factorial, the m factorial and the n minus m factorial in our expression for the binomial distribution. Okay, so we apply Stirling's approximation to the 3 factorials in our expression for the binomial distribution. And thus we rewrite our expression. And several different things happen in this step. First of all, we have these factors of ph to the m, 1 minus ph to the n minus m. Those factors go through unchanged. Next, Stirling's approximation contains a factor of the square root of 2 pi. We're going to get a factor of the square root of 2 pi from the n factorial, and then we're going to get 2 factors of the square root of 2 pi in the denominator from the m factorial and the n minus m factorial. When you take all 3 of those together, that gives one factor of 1 over the square root of 2 pi. Next, from the n factorial, we're going to get a square root of n, and from the m factorial and the n minus m factorial, we're going to get square roots of m and n minus m in the denominator of our expression. Next, from the n factorial, we get a factor of n to the n. From our m factorial, we get a factor of m to the m in the denominator. And from the n minus m factorial, we get a factor of n minus m raised to the power of n minus m, again in the denominator. Okay, lastly, we get a factor of several exponentials. Those factors are e to the m, e to the n minus m, and in the denominator, e to the n. Okay, so now we have our new expression for the binomial distribution as taken from the previous slide. First, let's look at those exponentials at the end of the second line. So e to the m, e to the n minus m over e to the n. Now, this is just equal to e to the minus n plus m plus n minus m. And that's just equal to e to the 0, which is 1. So we can drop that factor. Next, let's look at that other factor in the second line, the n to the n over m to the m, n minus m raised to the power of n minus m. Let's see what we can do with that. Okay, so let's do some manipulations on n to the n over m to the m, n minus m to the n minus m. Now let's remember that the average value of m, written as m in brackets, is equal to nph. Also, the standard deviation of m is equal to the square root of nph 1 minus ph. Now, the standard deviation is approximately about how much m typically differs from its mean value. So let's write m as nph plus delta, where delta is typically of order the square root of n ph 1 minus ph. So delta is much less than n. This should let us make some useful approximations. Let's also write 1 minus ph as pt to simplify the notation. Remember that ph equals the probability of a flip coming up heads, and pt equals the probability of it coming up tails, so ph plus pt equals 1. Okay, so writing m equals nph plus delta, and therefore n minus m equals n minus nph plus delta, which equals n times 1 minus ph minus delta, which equals npt minus delta, we get that n to the n over m to the m, n minus m to the n minus m, equals n to the n over nph plus delta raised to the power of nph plus delta times npt minus delta raised to the power of npt minus delta. Now again, ph plus pt equals 1, so nph plus delta plus npt minus delta equals n. This lets us divide the top and bottom of this fraction by n to the n. Okay, so in the numerator, the n to the n gets divided by n to the n and becomes 1. In the denominator, the nph plus delta raised to the power of nph plus delta becomes ph plus delta over n raised to the nph plus delta, and the npt minus delta raised to the npt minus delta becomes pt minus delta over n raised to the npt minus delta. So basically what has happened is we've taken nph plus delta factors of n out of the first factor in the denominator, and we've taken npt minus delta factors of n out of the second factor in the denominator. And finally, we can make this slightly prettier by getting rid of that fractional form and changing the sign in the two exponents. So now we have that n to the n over m to the m, n minus m to the n minus m, equals ph plus delta over n to the power of minus nph plus delta times pt minus delta over n raised to the power of minus npt minus delta. Now let's also pull minus nph plus delta factors of ph out of the first factor and put them out front, and pull minus npt minus delta factors of pt out of the second factor and put them out front. This gives us that n to the n over m to the m, n minus m to the n minus m equals ph to the negative nph plus delta, pt to the negative npt minus delta, times 1 plus delta over phn raised to the power of minus nph plus delta times 1 minus delta over ptn raised to the power of minus npt minus delta. Now we're going to use the relations x equals e raised to the power of the natural log of x and e to the x raised to the power of y equals e to the xy. So our expression currently contains a factor of ph raised to some power, a factor of pt raised to some power, and a factor of 1 plus delta over phn raised to a power, and a factor of 1 minus delta over ptn raised to a power. So we're going to rewrite 1 plus delta over phn as e raised to the power of the natural log of 1 plus delta over phn. And we're going to rewrite 1 minus delta over ptn as e raised to the power of the natural log of 1 minus delta over ptn. So this gives us ph raised to the power of minus nph plus delta, pt raised to the power of minus npt minus delta, times e to the minus nph plus delta natural log of 1 plus delta over phn times e to the minus npt minus delta natural log of 1 minus delta over ptn. Now this looks terribly complicated right now, but it will simplify down a lot quite soon. We're now going to use the series expansion of the natural log of 1 plus x. So as long as the absolute value of x is less than 1, the natural log of 1 plus x is equal to x minus 1/2 x squared plus 1/3 x cubed, etc. We're now going to apply this to the natural logs inside the exponents of our expression. So we're going to approximate the natural log of 1 plus delta over phn as delta over phn minus 1/2 delta over phn squared. And we're going to approximate the natural log of 1 minus delta over ptn as minus delta over ptn minus 1/2 of delta over ptn squared. In both cases, we've only used the first two terms in the series expansion. This substitution yields the following. So here, first we show the previous expression that we had for n to the n over m to the m, n minus m to the n minus m. So it contained a factor of pH to some power, a factor of pt to some power, and two exponentials. So here we've then rewritten that expression, substituting in the series approximations for the two logs in the exponentials. So now we're going to multiply out the terms in the arguments of the exponents. And we're going to drop terms that are suppressed by small factors of, say, 1 over n or 1 over the square root of n. And keep in mind that delta is roughly of the size of the square root of n. Here we've rewritten our expression from the previous slide. It contains two exponents. Let's take a look at the first exponent. So it's e to the minus nph plus delta times delta over phn minus 1/2 delta over phn squared. So the argument of this exponent contains two factors, and each of those factors contains two terms. So when we multiply them out, we would expect to get 4 terms in total. However, when we multiply the delta from the first set of parentheses times the minus 1/2 delta over phn squared from the second set of parentheses, we get something that goes as delta cubed over n squared. And that's suppressed by a factor of 1 over the square root of n. A similar thing happens in the second exponential. So at the bottom of this slide, we've given the results of multiplying out these terms. You might want to pause the video here and see if you can convince yourself of these expressions. Now let's look at our new approximate expression for n to the n over m to the m, n minus m to the n minus m, and see how it simplifies. So it contains a factor of pH raised to some power, a factor of pt raised to some power, and two exponentials. Let's take a look at those exponentials and see how they simplify. So first of all, the first exponential contains a factor of e to the minus delta, and the second exponential contains a factor of e to the delta. These two factors will cancel, and so we can ignore them. Next, let's look at the first exponential. The argument of the first exponential contains minus delta squared over phn plus 1/2 delta squared over phn. These just add together to give minus 1/2 delta squared over phn. Similarly, in the second exponential, the minus delta squared over ptn and the plus 1/2 delta squared over ptn add together to give minus 1/2 delta squared over ptn. Next, we can note that 1 over pH plus 1 over pt equals pH plus pt over pH pt, which just equals 1 over pH pt. So this gives us that n to the n over m to the m, n minus m to the n minus m is approximately equal to pH raised to the minus nph plus delta power, pt raised to the minus npt minus delta power, e to the minus delta squared over 2 pH pt n. We can now substitute our newfound approximation for n to the n over m to the m, n minus m to the n minus m, back into our expression for the binomial distribution formula. So just to remind you, that formula had some factors of pH, some factors of 1 minus pH, a 1 over the square root of 2 pi, a square root, and then this factor of n to the n over m to the m, n minus m to the n minus m. Now, when we perform that substitution, something magical happens. Now remember, we had these factors of pH to the m and 1 minus pH to the n minus m. The expression that we've just substituted in contained factors of pH to the minus npH plus delta and pt to the minus npt minus delta. But note that m equals npH plus delta, and n minus m equals npt minus delta, so all of the factors of pH and pt cancel, and we get that p of m, given pH and n, is approximately equal to 1 over the square root of 2 pi times the square root of n over m, n minus m, times e to the minus delta squared over 2 pH pt n. Okay, so there is still one more simplification that we can do. Remember that m equals pH times n plus delta, and n minus m equals pt times n minus delta. So this square root that we have in our expression, the square root of n over m, n minus m, can be written as the square root of n over npH plus delta times npt minus delta. Now, those terms delta are small compared to npH and npt, so we can neglect them, and this becomes the square root of 1 over npH pt, up to terms of order delta over n. Therefore, our expression for p of m, given pH and n, simplifies slightly by replacing the square root of n over m, n minus m, with the square root of 1 over n pH pt. Now, finally, let's put this back in terms of m instead of delta. So now we have that the argument of the exponent is minus m minus npH squared over 2 pH pt n. Okay, so we have that p of m, given pH and n, is approximately equal to 1 over the square root of 2 pi n pH pt times e to the minus m minus npH squared over 2 pH pt n. Now this is the result that we're looking for. But let's note that a function of the form here written as f of x given mu and sigma, 1 over the square root of 2 pi sigma squared e to the minus x minus mu squared over 2 sigma squared is called a Gaussian, or normal distribution. So for large n, the binomial distribution approximates a Gaussian with mu equal to npH and sigma equal to the square root of n pH pt. Okay, so let's summarize. Here we've talked about the binomial distribution in the limit that n gets large. We see that it approaches a Gaussian distribution with mu equal to n pH and sigma equal to the square root of n pH pt. This will be a very useful and convenient result. In particular, we'll be interested in using this for understanding Gaussian error bars. If you would like to know more about the binomial distribution or the Gaussian distribution, or the closely related Poisson distribution, you might want to check out other videos on this channel.